So in the part one, we left where we can see the position from the velocity using by the fundamental calculus theorem and expressing a function of t in terms of the initial position plus the integral of the velocity or the displacement over the interval 0 to t. So let's see one example of how that operates. We have a block that hangs at rest from a massless spring at the origin, as you can see here in the picture. At t equals 0, we're going to pull the block downward 1/4 of a meter to his initial position. So S of 0 is going to be minus 1/4, and it's going to be released. The velocity on miles per second or meters per second is going to be given by b of t equals 1/4 of sine of t. And this is going to go for t that is positive. Let's assume that the upward direction is going to be positive in the movement, and going down is going to be negative. So we can relate the setup as follows. We have the block hanging here from the spring, and because we're moving it 1/4 from the original position, you can see that it's going to be below the zero. Positive units are going to go over here, negative units are going to go below. So now let's find the position of function of the block. Since we have the velocity function, we should be able to do that. Then we find the graph function b and when it's going to happen for the origin for the first time. So the first thing is that the velocity function is given by the function 1/4 and then sine of t. As you can see, we're going with the sine function, but now we're oscillating in the period from 0 and onward up to 3 pi. And so we can just go ahead and compute what is going to be my position function. Remember that everything is going to be in terms of the initial position, which is minus 1/4, and this function here. So if I'm expressing the function with the formula we just saw, s of t is equals s of 0, 0 to t of 1/4 of sine of t dt. Okay, this is supposed to be a plus. So this is minus 1/4 plus, and the integral of this is going to be minus cosine. So 1/4 minus 1/4 cosine of t. And now this antiderivative goes between 0 and t. Therefore, we're going to have notice that cosine of 0 is 1, so we're going to get 1/4. That 1/4 is going to cancel with this, and we're going to obtain that our function s of t is minus 1/4 cosine of t. So now this is going to be my positioning function. If you consider the areas, the displacement up to 2 pi is going to be 0, and the distance traveled will be 1. That using, of course, what is the displacement and completing a full circle is going to give me 1. And the position function is going to be given by minus 1/4 cosine of t, which is given by this particular graph over here. So essentially the procedure is as I presented here. You just have an integral that is in terms of the initial position and the velocity, and after integrating, you can get a specific function to dictate that. Now, this procedure is not necessarily done with functions that they need to be strictly continuous. We can do this with functions that are piecewise function, as you can see in the following example. We're going to have a skydiver that leaps from helicopters and falls straight in a straight line. Assuming he reach a terminal velocity of 80 meters per second, immediately at t equals 0 and falls 19 seconds, at which time he's going to open the parachute. The velocity is going to decrease linearly 6 meters per second over a 2-second period, and then remain constant until it reaches the ground at t equals 40. So the motion that I just described is represented by this function here. So initially it goes terminal velocity of 80 meters per second the first 19 seconds. Then after that, by 2 seconds, is going to go over a linear relationship, reducing, and then after that is not going to have any change on the velocity. It's going to be constant velocity until it reaches the ground at 40. Now, with this, we can determine the height above ground that the skydiver jump. We have the initial position, of course, and from this is only a matter of calculating the distance traveled. So we consider the absolute value of the function b of t from 0 to 40. Then what's going to happen is that we can split this into the different areas. So from 0 to 19 is just going to be 80, and is this full area. From 19 to 21 is just going to be given by this line, which is going to connect this and this point. And from 21 to 40 is just going to be given by a constant velocity of 6, which is the velocity that is going to maintain in the last part. By the way, this is supposed to be 6 instead of 0. So at this point, we integrate over the different intervals, and then once that we obtain what each of these areas measuring, notice that all these are positive areas, so they're going to add up to the movement, and adding up what this result gives me is going to give me the full distance that is traveled. Now, in a similar fashion to what we did, we can calculate the velocity from the acceleration. Yeah, we can calculate the position from the speed. So it stands to reason that we can do the same thing with the other relationship. So we can find the velocity in terms of the initial velocity plus the acceleration in a certain interval of time. So following this formula, let's take a look to an example. You can have an artillery shell is fired directly upward with an initial velocity of 300 meters per second from a point 30 meters above the ground. So something more or less like in the picture. So assume that the force of gravity is the only thing that is acting on the shell, and it produces an acceleration of 9.8 meters per second square, which is the normal approximation of the gravity. Let's find the velocity of the shell while it's in the air. So here we want to find out what is the velocity function. Now notice that we have certain things. We have the acceleration, which is given by the gravity. We have the initial velocity, which is given by 300 meters per second. And we have an extra of the initial position with 30 meters. Now, to find out what the velocity is, we consider that the positive direction is, of course, going up, corresponding to the ground. And because the initial velocity is 300 meters per second, then we can just replace that as the initial velocity here. The acceleration due to gravity is downward, so it gets a negative value here. So we're going to have that the speed is given by 300 minus 9.8t. This is going to be represented by this graph over here. And as you can see, this is going to reach the maximum point, or so the point where the velocity gets to be 0 at 30.6 seconds. Now, notice that that's the general velocity of the shell while it's in the air. And with that, you can find out more information, even if you need. You can find out the speed, the positioning from here. And with that, you're going to be able to tell when the maximum height is found at this point. And also, you can probably get an approximation of when it's going to hit the floor. Now, on this integral approximations, there's a more general situation that can be expressed, and is the net change and the future value. And in summary, the net change is only checking what certain rate of change is producing over an interval of time. So let's say if a quantity Q that can be represented in anything changes over time at certain rate Q prime, then the net change is just going to be given by the fundamental calculus theorem. And the integral of a to b of q prime is just going to represent q of b minus q of a, which is going to be the net change of q on those particular values. Now, in a similar fashion to what we did with the speed and acceleration, we can find the future value by just considering that we have the quantity q given by the initial quantity q of 0 plus the rate of change over a certain interval of time t. And that will produce what the future of q is going to be at that point t. So in summary, there is a correspondence between velocity, displacement, and acceleration problems. In a more general way, you can consider that as change, net change over a certain quantity, or a future value for a specific quantity or function that is representing a change. So the most common application is the velocity displacement, where the position is s of t, the velocity is s prime, and of course the acceleration is s2 prime. And then you can get the displacement and the future position of the function. In a more general way, you can do that with net change and the future value of q. One example of this will be as follows. We have a cell growth study, and a culture of cells in a lab has a population of 100 cells when nutrients are added at t equals 0. So notice that this is going to be the initial value. Suppose that the population n of t in cells per hour is going to increase to a rate of n prime equals 90 exponential to minus 0.1 t. We want to find out what n of t is. Of course, we're going to use the formula of the future value, and n of t is going to be given by the initial value plus the integral from 0 to t of n prime of x. Doing that, we have that n of t is going to be 100 plus 90 over minus 0.1 e to the minus 0.1x between 0 and t by the fundamental calculus theorem. And simplifying that, this is just 1000 minus 900 e to the minus 0.1 t. Notice that this growth rate is initially 90 cells per hour, and it's going to decrease as time increases until the point where the growth rate is going to stabilize at certain rate close to 0. And the graph of the population function that we just presented shows that the population is increasing but to a decreasing rate. So that means that eventually it's going to stagnate and is going to reach a maximum population. Okay. The number n of 0 equals 100 cells is satisfied, and the population's size is going to approach 1000 cells as we go towards infinity, or as we go to big time. All right, so this is the final examples of the applications of the integration. Very related to the same applications of the integration of the derivative that we can do with position functions. It's just we're going this time in the reverse order to what we usually could get in derivatives. In section 6.2, we're going to be checking how to analyze areas between different curves and how do we use the integral to find that out.